Now let's take a look at mapping shadow properties in practice. In the upcoming demo, we'll investigate how we can change the checksum property of the customer entity so that it's mapped as a shadow property instead of directly on the customer instance. We'll also look at how we're still able to access the data in the checksum column using AF_Core's change tracker. So while the examples that we just saw during the slides were all about how AF_Core will automatically infer shadow properties for us under the covers, the demo that we'll look at now will show us an example of how we can work with them by directly taking advantage of this feature and defining our own shadow properties. We're now inside Visual Studio and we're looking at the customer class. As we can see here, the checksum property has been commented out. It was never mapped to the database to begin with, and therefore it hasn't been part of any Code1st migration that we've created. So this is not something that will affect any new migrations that we create. But if we take a look here in the Server Explorer, we can see that the development team at Craftwork has added a var binary column on the customers table called checksum. If we look at the table definition for the customers table, we can see that the checksum column is a computed column that returns a var binary value that has a size of 1024. And if we look at the formula for the computed column, we can see that it uses SQL Server's built-in checksum function to generate a checksum based on the first and the last name and the username. This is then converted to a var binary so that we can store the value in a byte array in our C# code. If we take a look at the data in the customers table, we can see that our two John Does now have a checksum property which contains a hexadecimal number which represents the checksum for each of our customers. But let's head back to our database context to see how this was set up. As we can see here, what the Craftwork team has done is to use the computed column SQL method, just like we did when we defined the computed value for the price after VAT field. But notice that we used the method differently in the two instances. When we defined the formula for the price after VAT column, we did so directly on the corresponding property on our customer entity. But since the customer entity no longer has a checksum property, we can't do the same for that property. Instead, we use an overload of the property method, where we set the generic type parameter to be a byte array and pass in the value checksum as the name of the property that we want to fetch data from. Just as an aside, it's worth mentioning that we could also have set up the price after VAT property in this way, as well as any of the other properties that we've set up here in the onModel creating method. But whenever we define something for a property that exists on one of our entities, it's much more convenient and more maintainable to use the method that accepts a lambda statement. But for the checksum property, we can't use that method, which is why we use the one where we explicitly name the property that we want to work with. And since that property is not backed by a field on our entity, AF_Core will set it up as a shadow property and solely maintain it using the change tracker. But let's head back to Visual Studio and just quickly notice that the Craftwork team has also created a migration file that can be used to set up the new column on the customers table. We know that they have already applied it to the database since we saw that the column existed on the customers table. And we won't spend any more time on this migration file since the mechanism for setting it up is exactly the same as it was for price after VAT. Instead, let's try to interact with our new property. We'll do so here in the program class for our GUI console project. So as we've mentioned, the checksum property is maintained on the AF_Core change tracker. So the first thing that we need to do is turn our request to fetch a customer into a request that tracks changes. Actually, unless we explicitly tell AF_Core to return non-tracking queries, the default is that the queries that it returns are tracking queries. In the code here, however, this has been made explicit by calling the asTracking method on our customers collection on the database context. The fact that this is a tracking query ensures that AF_Core will track any changes that we make to the entities that we fetch with this call, and it will also give us access to the checksum property. So the first line of code here fetches the first customer from the customers collection on the database context. In the following line of code that we see here, we fetch the checksum property of this customer by first fetching its change tracking entry by using the entry method, and then getting the value from the specific property by calling the property method and passing in the name of the checksum property. The object that we get back here can be used for several other things related to maintaining the state of the entity. But for our purposes, we just need the value that it currently has. We take that value and cast it to a byte array, which we store in the checksum variable. Note that even if we didn't cast the value returned to us, the underlying type of the value of the property is still a byte array. But since the current value property returns an object type, we need to cast it. Also note that the current value could very well be null. So in a production setting, we should of course guard against that. The next bit of code that we see here actually just fetches the checksum property again, but does so using the static property method on the EF class. The EF class contains several other helpful methods, so it's well worth the effort to become acquainted with this class. So in order to fetch the checksum using the ef.property method, we set the generic type parameter to be a byte array and pass in the entity that we would like to work with and the value checksum as the name of the property that we want to fetch data from. As of the most recent version of EF Core, the ef.property method can only be used inside LINQ queries and cannot be used to access the value assigned to a property in other scenarios. This is why we show it here inside of a select statement. Also note that we explicitly set up the query to be non-tracking. This would not have worked in the example above where we fetched the value using the entity's entry on the change tracker. Had we used a non-tracking query for that, the current value would have been null. But the ef.property method, on the other hand, works both with non-tracking and tracking queries. This, and also the fact that it can be included rather elegantly inside a LINQ statement, means that this may often be a convenient way of fetching data from a shadow property. In the next line of code, we use the BitConverter class to convert the byte array in the checksum variable to a hexadecimal string so that we can compare it to the value stored in the database. Also note these last few lines of code. They show how you would ordinarily update the content of a shadow property. Because checksum is a computed column, this will not work. The call to the SaveChanges method on the database context will not actually fail, but it will not have any effect and the checksum for our customer will not be changed on the database. Had it instead been an ordinary column such as first name that we had set up as a shadow property, we could have used code like this to update it, and also update the data on the database by calling SaveChanges afterwards. It's of course very important to be able to update shadow properties, so if you'd like to see an example of how to do this in action, I suggest you check out Julie Lerman's EF Core 6 Fundamentals course, where she has a great demo showing us how to do this. But since these lines won't actually do anything, let's instead comment them out and try to run the code. So the first line of code here fetches the first customer in the customers collection. And if we advance the debugger one step, we can see here in the watch view that it is John Doe with ID 4 that we get back. If we take one more step with the debugger, we fetch the checksum data for John Doe from the database. And here in the watch view, we can see the content of the byte array that we've cast the data to. Taking one more step with the debugger will fetch us the checksum once again, but this time using the ef.property method. And as we can see here in the watch view, the result is exactly the same. If we take one more step with the debugger, we convert the byte array that we just fetched to a hexadecimal string, which we can compare to the value stored in the database. We'll do so by once again looking at the contents of the customers table in the database. And as we can see here, the value that is stored in the database is the same as the value that we have in the watch view, except that they are formatted somewhat differently, and the database value has the 0x prefix in front of the value. In the demo that we just watched, we saw how we can set up shadow properties in our EF Core data model. This allowed us to access data from database columns that were not backed by a field in our entity classes. While shadow properties are mostly something that EF Core uses behind the scenes to, for example, facilitate temporal tables or to keep track of foreign key IDs that we haven't mapped explicitly, we can also use them ourselves to access other fields that are not mapped on our entities, but which exist in the corresponding tables on the database. We saw how this could be set up in the onModel creating method in the CarvedRock database context. And we also saw how to access the data from the shadow properties using EF Core's change tracker, or alternatively in a LINQ statement using the static ef.property method.